solution for some question in paper 1, which is difficult. The first question here, we have a vibrator attacked on a ceiling something. At the bottom of this vibrator, there's a string and there's a wave generated by the vibrator on the string. It is very important to pay attention to the word phrase here. The first harmonic of the standing wave. It means that this wave, the standing wave on the string from one wave packet like this, one wave packet, with the end here is fixed at one boundary free. Okay. The bottom is free. This is the fixed point. The top is the fixed point. The bottom the free point. So the free point always oscillate as the antinode, meaning we have a wave packet like this. The full wave packet is like this, with the two nodes at the top and bottom. But the free end here only is the antinode, okay? And the distance here between a node on a fixed point and the antinode at the free point here, the distance here is lambda over 4. So we have lambda over 4, 1/4 wavelength equal to 3 meter. So the wavelength is 4 times of 3, 12 meter. And the wavelength is equal to the speed of the wave, which we need to find how many, divided by the frequency f. And we know that the frequency is 300 hertz, and therefore the speed is 12 times 300. Paper 1, not calculator. 12 times 300 is 36 something. Okay, so the answer 36 is here. Answer D, okay? Answer D. Question 1. 3,600 meter per second and converting to kilometer per second. The next one, stopper mass A gram leaves the opening of the container containing pressurized gas. Stopper, okay. We have a bottle like this containing the gas at high pressure, and we have a stopper here, like a alcohol bottle containing champagne, for example. And this stopper leaves at the speed 20 meter per second. The mass is 8 grams. So there's something like this is a problem about momentum, because we are given the mass and the velocity. The stopper accelerates from rest for time 16 milliseconds. We already know the time 16 milliseconds. Of course, we need to convert it into the SI unit, 16 times 10 to negative 3 meter second. The speed, 20. So we have the change momentum. The question is the order magnitude of force acting the stopper. We have a formula in the data booklet, which is the force equal to the change of momentum divided by the time. Or another form in booklet is the force multiplied with the time is the change in momentum. And the product, force multiplied, is called the impulse. And in this problem, we need to find the magnitude, the force, change momentum. Initial momentum is 0. Final momentum is 8 gram multiplied with the speed. Of course, we need to convert this 8 gram into kilogram, 10 to negative 3 kilogram, multiplied with the speed 20, and then divided by the time 16 times 10 negative 3. So negative 3 cancel each other out. We have 8 over 16 is 1/2. 1/2 and 20 divided. 20 multiplied with 1/2 is 10. So it's about 10 newtons. And therefore the answer is this one, 10 newton. Yes. Okay. Remember to convert the unit to kilogram and the time to second. The next thing, an object projected vertically upward with the time t0 and resistance negligible. The object passes through the same point above the starting position at the times 2 seconds and 8 seconds. Projectile, the same point above the starting position. Okay, projectile motion like this with the starting point we can call it O, like the origin of our coordinate system, passes the same height, the same point above starting position, vertically upward. Okay, sorry, it's not a curve. It is projected directly vertically upward, vertically upward. It's okay. This is the starting point. It reaches certain height like this at this point. At the same time, 2 seconds going up. It takes 2 seconds to go up to that position, and then continue going up to very high until the velocity decreases to zero, and then fall back again, passing through this same point. After another 6 seconds, going up 3 seconds, going down 3 seconds. The total time going up and down 6 seconds, and the total time from the starting time when we start shooting it up is 8 seconds. What is the initial speed? The fastest way to solve this problem actually very simple. We just need to focus that uh, the time here is 2 seconds. And because the g gravitational acceleration is taken as 10 meter per second squared, it means that the velocity will the total time going up is 2 seconds going to this position. Let's call this position A. Okay, it takes 2 seconds to go to this position, and then it takes another 3 seconds to go to the top, and then 3 seconds to fall back again to position A. So the total time is 6 seconds going up from A to the top B. Okay, 3 seconds going up from A to B, and then 3 seconds falling down from B to A. And so we know that the total time of this object goes from the starting point to the top is 5 seconds. 5 seconds. So that the velocity, initial velocity u decreases to zero in 5 seconds. And we have the formula V. You can check the topic 2.1, the formula in the booklet. V is u plus at. U is what we need to find. V is 0. And A is negative 10 because V is going up and the velocity is decreasing when going up, and the time t, and therefore the time we already determined the time is 5 seconds, and therefore the velocity u must be 50 meter per second. Okay, 50, answer A. The next one, alternating current AC generator produces a peak EMF E0 and periodic time t. What are the peak EMF and periodic time when the frequency rotation is double? Peak EMF frequency double. AC generator. Okay, the AC generator, it works on Faraday's law about inductions, electromagnetic induction. So the EMF generated by the generator is proportional to the rate of change of the magnetic flux. The change of magnetic flux divided by the time, the rate of the change, and also involve a negative sign, meaning if the EMF, the change of flux is negative, meaning the flux is decreasing, the EMF is positive in the opposite direction, the Lenz's law. Anyway, it's proportional to the rate. This is the rate of the change in the flux of flux change. And therefore, when we increase, when the frequency double, it means the speed of rotation, the time here will be shorter time. Therefore, we will have a greater EMF, double frequency. Double frequency from F to 2F, it means increasing the speed, faster rotation of the generator, faster rotation. And therefore, the EMF here will be twice the EMF. Wait. The same. What are the peak EMF and periodic time when the frequency is double? I don't think it is your answer here. The EMF is proportional to the speed, the rate of the flux change. Therefore, double the speed will make the EMF twice, meaning the answer is 2E. We will eliminate this thing. And the period, of course, we have the period is the inverse of the frequency. Double the frequency will make the period to be halved. So the answer is this one. Okay, answer B. 34. The plane of the coil position at the right angle to a magnetic field flux density B. The coil has n turns. Mm. Each area A, the coil is rotated through 180 degree in the line T. Okay, like this. So the flux of the magnetic field B passing through this coil will increase and decrease from a certain value to zero to maximum, then to zero again sinusoidally like this. A sine function, a sine function. Um, what the magnitude induced EMF? Okay, rotated through 180 degree. Okay, it's rotated 180 degree, meaning from this position rotate 180 degree. Look at my hand here. My hand here. Okay. Initially, it is like this. The field is pointing toward the coil like this, and then I rotate this one 180 degree. This is the field, magnetic field B. Okay. Rotate this coil 180 degree, meaning flipping it like this. Okay, so during this flip, the flux from the maximum flux here at the initial time, maximum flux decrease to zero flux here, and then increase to maximum again. The flux vary like this. From maximum, I will draw the graph. From maximum value here, phi max decrease to zero, and then increase again, but in the opposite direction when this coil is rotated 180 degrees. The induced EMF, according to Faraday's law, the EMF equal to the rate of change in flux. Mm. And again, the flux has a direction. The formula for the flux is pi equal NBA times sine of the angle between the field and the normal line of this coil. Initially, we can choose the normal line to be in this direction. Sine of zero. No, sorry. It's not sine. It's cosine. Cosine. Initially, this is n, the normal line, the normal vector of this coil, the surface. The field is pointing toward the surface like this, pointing toward it, perpendicular to the surface, which means the initial angle between the field and the normal line here is 0 degrees, and therefore the cosine of 0 is 1, and the initial field, initial flux is maximum, which is NBA. The final flux, final. When rotating this coil, the coil is rotated 180 degree. The angle become 180 degree, and therefore cosine of 180 degree is -1. And other thing, NBA is the same. So we have the final flux is NBA times -2. And the change in flux delta pi is the final flux subtract the initial flux, and therefore we have the minus NBA here, minus NBA, minus NBA initial flux again. Sorry, this initial flux NBA again, and therefore you have -2 NBA. Okay, the change in flux is -2 NBA, and according to the equation of the EMF here, EMF is the negative of the change in flux over the time of that change. The time is t, not delta t. Even here, the time in the time is just t, okay, not delta t. The change in flux is -2 NBA, and another minus sign in front of it, making it positive, and therefore that is the reason why the answer is D. Okay, it is very important to use the Faraday's law here. This formula is also given in booklet, of course. Check it. Yeah, and I see that this is a difficult topic, of course. I know a lot of students struggle with the kind of question. Therefore, we need to practice with the topic 11 about induction and Faraday's law. The next one, excuse me for a minute, huh? Okay. The next one, a charge negative C is moved from A to B, then back to A. The electric potential at A is 10 volts, and potential at B is minus 20 volts. When the work done in moving the charge from A to B, and the total work done. Okay. Firstly, the work done to move the charge from A to B is equal to the charge, the charge Q, multiply with the potential difference between A and B. But I wonder that is the potential difference between B minus the potential at B minus potential at A, or the other way around. It means Q times VA minus VB. But let me check it. I definitely can figure it out. Um, the potential at A is higher, positive 10 volt, and at B is lower, minus 20 volt. The charge is minus 3 coulomb, meaning this is a negative charge, and therefore um, the negative charge will automatically move in the direction from, okay, the electric field, the electric field like this, E, the field always point from a positive charge to a negative charge, meaning from higher potential to lower potential, higher potential V to lower potential V. If it is a positive charge, it is repelled by this electric field moving toward the negative potential, like the water falling from a certain height, from a cliff to a waterfall. Okay, but a negative charge is attracted toward the positive charge. These like charges attract each other, meaning the negative charge is naturally, spontaneously uh, attracted by the electric field to move from lower potential to higher potential. Anyway, along the answer, we have the work is always the positive value. Positive, they have no negative value. So just take this thing, the difference in potential, minus 20, minus 10, and then multiply with the charge minus 3. Okay, we have the work. Minus 20 minus 10 is minus 30. Minus 30, and then multiply with 3, that is 90. So the answer is 90. We don't care about these 230 anymore, okay? The work done when returning to A, it is like the work done by any force when moving in any arbitrary path going back to the starting point. The total work done is 0, and therefore we will choose this one. Total work when returning to the starting point, okay? Starting point, total work is 0. Answer C, okay? And this formula, the work done equal to the charge multiplied with the potential difference. Of course, it is given in the booklet. It is given like, let me check that. Given like delta V equal the work over the charge. Okay, delta V is a potential difference. Potential difference. Work done by the electric force to move that charge between the 2 points in a circuit. Check the formula booklet to find with equation again. 27. A spring loaded with the mass m oscillate with a simple harmonic motion. The amplitude of the motion A, and the spring has a total energy E. What is the total energy of the spring with the mass increased to 3m and the amplitude increased to 2a? We have this following equation for calculating the energy of a simple harmonic oscillation. One half k a squared, where a is the amplitude, and k constant, the coefficient of proportion, depends on the mass of the object, and the spring constant increased to 3a, mass increased to 3m. The k here is proportional to the mass of the object. and also proportional to the spring constant. This K in the formula is not the spring constant. Wait. It is the spring constant. Let me check the booklet for a minute, huh? The physics booklet. Hmm. This is topic 4 about, wait, topic 9 about oscillation, or topic 4. I'm checking that. Yeah, topic 9. We have the formula for the energy, kinetic energy omega. We have the formula omega, but we don't know pendulum's mass spring. Okay. There's an equation in the formula booklet like this. Let me write down. The total energy is 1 half m omega square times x zero square. Let me write it again, huh? In the booklet, topic 9.1 about oscillation, topic 9.1, okay? The total energy is 1 half m omega square times x zero square. X zero here is the amplitude. Omega here is called the angular frequency, and it is equal to 2 pi f, or 2 pi over the period, in which the period of the oscillation of this spring oscillator, the period is 2 pi square root of k over m, where k here is the spring constant k, okay, the mass m. Now we triple the mass, here 3 times. The period will be square root 3 times lower, and therefore the omega here will be square root of 3 times greater, okay, 3 times greater, and we squared it here, and therefore the total energy will increase by 3 times, because of the decrease in the period due to the increase of the mass here, okay. And one more thing, the amplitude increased by 2 times, and therefore we need to multiply with the square of 2. We also have a square here for the amplitude, square of 2, okay? And therefore it is equal to 3 times 2 square, which means 12 times compared to the initial energy, okay? Initial energy. And therefore the answer is 12A. Kind of difficult, huh? If you see a question like this, you can skip it, because again, in paper one, we have 40 questions. You just need to get about 33 to 35 questions to get an A, to get a 7. Okay, 30. I think 33 to 35. Yeah. 28. Monochromatic light is incident on an identical slit to produce an interference pattern on a screen. One slit is then covered so that no light emerges from it. What is the change to the pattern observed on the screen? I've seen quick question like a few years ago, pretty recent, not very long. Okay, there is no change in the separation between the slit. The distance between the maxima is the same. The only difference is the intensity, yeah, of the maxima, and therefore the outer, because we have a pattern like this, maxima, and then maxima, and then maxima, and then maxima. Okay, and we have a what's it called? Um, diffraction boundary. Anyway, the point is when one slit is covered, the intensity of light passing through only one slit, now, that intensity is lower than the intensity when we use the two slits, because two slits we have more area, more way pass for the light to pass through, and therefore the resultant pattern will have greater intensity. But when we cover one slit, the amount of energy amount light passing through one single slit. And anyway, now it becomes single slit diffraction, not the interference of double slit anymore, and therefore the new pattern will have less maxima, and lower intensity. Fewer maxima will be observed. Okay, I'll send you a picture. Let me try, inserting a picture here about the difference between single slit diffraction and double slit interference. Yeah, I'm looking for a picture of that. Difference between these two. Okay. Oh wow. Let me take this picture, put it here. Hmm. Okay, here. The slit width is 50 micrometer. With one slit, we have a wider pattern like this. I mean, wider width of a maximum in the middle here, single slit, huh? And the separation here between the slit, between the maximum is like this. And for the double slit, we have this pattern with a much shorter pattern. Okay, so in conclusion, when covering one slit, we have this kind of pattern, which means um, it has the wider width for the maximum, the central maximum, and also less number of maxima. We have only three maxima here, not as many like the second pattern for the double slit. Okay, the next one, 19, huh? I suppose so because I don't see the question about 18. Satellite X of the mass m orbits the Earth with a period t. What will be the orbital period of satellite Y of the mass 2m occupying the same orbit at X? Orbital period of satellite Y of mass 2m occupying the same orbit at X. Period t. The mass 2m. As I remember, the period of a satellite is independent of the mass. I can run like this. The period does not depend on the mass, meaning it will have the two satellites will have the same period as long as they are on the same orbit, the same distance from the center of the Earth. Okay, if you can remember this thing, you can do it quickly. If you don't, there's another way, which is more complicated. We need to find the formula for the period of a satellite. That period is the length of the path distance, which is 2 pi r, the circumference of a circle. Okay, we assume that the orbit of the satellite is a circle. So this path length divided by the speed of the satellite v, we have the period. And the speed here is determined by a formula, an equation. Gravitational force G big M small over R square. Big M is the mass of the Earth, M is the mass of the satellite. This is the formula for gravitational force. Okay, this gravitational force is the centrifugal force, the mass of the light times the square of its speed divided by the radius. From this formula, we have the speed equal to gm. We simplify m here, huh? And simplify r also with the square here. Gm over r and then square root it, and then plug back into here again to get the formula for the period. 2 pi r over square root of gmr. And then we will move the r here at the bottom to the top. We have 2 pi r times square root of r, or we can write r power 3 over 2 over square root of gn. Okay, and as you can see that this period only depends on two things, actually three things. No, two things, sorry. Because mg gravitational constant is constant, it only depends on the distance from the satellite to the center of the planet and the mass of the planet. And it does not depend on the mass of the satellite. And therefore, as long as the two satellites have the same distance to the center of the planet, they have the same period. Okay? Same period. Question 16 here about Kirchhoff's law. We have a circuit like this, pretty simple. Parallel resistors and a current. Excuse me for a minute, huh? I need to check this message from the customer. Kirchhoff's law applies to circuit with the equation for the dotted loop. Dotted loop. The current I1 getting into this node, this point is called a node. Okay, the current I1 getting into this node will be equal to it will split into the two components, I2 on the top and I3 at the bottom. So we basically have an equation I1 getting into it equal to I2 plus I3. This is Kirchhoff's first law. Okay, the Kirchhoff first law. Um, Equation dotted loop 6 6 volt is the voltage of the battery, and of course we can calculate the total resistance of the circuit. Okay, uh, I2 multiply with 3 ohms here, the resistance here. I2 multiplied with 3 ohm will be equal to I3 multiplied with 4, the resistance at the bottom. And I1, okay, okay. The second law, of the Kirchhoff is the voltage of the battery, 6 volt, EMF actually, because the internal resistance here is 0, so the EMF is equal to the voltage, 6 volt. 6 volt equal to the total voltage of the components, which is the voltage across this resistor, which is I1 times 2. 2 is the resistance, okay, time I1, and add it with the voltage of this branch. The voltage of this branch, it just need to calculate one, one volt value, one voltage, meaning I2 times 3 or I3 times 4. And according to the option ABCD, we have the last one, I3 times 4. I3 times 4. This is the voltage of the this branch. The two resistor, 3 ohms and 4 ohm, they have the same voltage, okay, because they are connected in parallel, and therefore the answer is D. The next one, we have a standing wave with the two points x, y having the same amplitudes on this standing wave, but the phase difference 180 degree. If we have another point here, x dash, another point, with x dash point with the distance lambda over 2 here, we have the same phase. Note that this is the standing wave, not the normal traveling wave, okay? Standing wave. And therefore, the distance between two points having the same amplitude and the same phase with each other on this standing wave is lambda over 2, not lambda as the normal wave. Anyway, x and y will have the phase difference to be pi over 2. Pi over 2. Um, wait. Pi over 2 or 0? No, it's 0. You put a sign here indicating that it's 0, huh? Oh, sorry, my fault. Okay, here. The difference between standing wave and the normal wave is that all the point on this standing wave in one packet like this, they oscillate with the same phase. X and Y here is moving down together with the same velocity also because they have the same amplitude. The one in the middle here, the top, later I'll send you a simulation about the standing wave to show that all these points inside one packet, they have the same phase. The particle on the top here, let's call the point Z here, will have a greater velocity, the greatest velocity, but going down as well, meaning all these points X, Y, Z, and if I consider any other point here or here or here, they have the same phase for the standing wave. Okay, I'll send you a simulation about this. And the particle on the packet here, next packet, they have the opposite phase going up like this, going up, meaning one point here, x here, and another point here, for example, m, we have opposite phase. The phase difference is pi, 180 degree. Okay, but all the point in one packet, they have the same phase. Which is a very weird, no, not actually weird, but that's it, a characteristic, the importance of sending wave. Okay. The next one, what neutron of mass m, a neutron mass m, is confined within nucleus diameter d, ignoring numerical constant, what is the approximate expression for the kinetic energy of the neutron? Hmm. Kinetic energy. This is a question about topic 12 about particle and quantum physics. Confined within nucleus diameter d. Okay. Uh, Confined inside this nucleus, we use the Heisenberg uncertainty principle. Heisenberg uncertainty principle, which means the uncertainty in position multiplied with the uncertainty in momentum is greater than or equal to uh, Planck constant over 2 pi. Let me check that formula again. Heisenberg uncertainty principle. Topic 12, huh? Uh, over 4 pi. Over 4 pi. H over 4 pi. And the diameter, the delta x here is the diameter d. So the uncertainty of the momentum, we can say is like the difference between the average momentum and the maximum momentum. is delta p will be equal to h over 2 pi d, because d is delta x, huh? And the uncertainty of momentum, kinetic energy of the neutron nucleus, delta v energy. The neutron does not move like an electron, like a particle and atom moving with a certain speed. The neutron is confined within the nucleus. Okay. There's some letter like M, or okay, the mass of that. Something, it has to do with the mass relating to, you know, energy and time. Actually, I don't know which one, huh? I get to you back to you later. After figuring it out somewhere, reading some website, asking other, experts. For now, we skip this one, huh? I'll go return later. The next one, 30A. In the Bohr model of hydrogen, an electron in the ground state has an orbit radius r and a speed v. In the first excited state, electron has an orbit radius 4 pi. What the speed electron in the first excited state? Okay, check the formula sheet booklet. We have another formula like this, MVR. In the topic 12, topic 12, we have the formula MVR. Which thing MVR is called the angular momentum, is equal to nh divided by, h is a Planck constant, n is an integer, divided by 2 pi, here. Okay. Check the topic 12, the data booklet, to have this formula. The reason is because I know that we need to use this formula is because we are given the radius r and the speed v. And we know that this is a problem about Bohr model, the problem about topic 7 or topic 12. So we need to check the formula in these two topics. If this is called, this formula is called a quantization of energy and of momentum. I sent you a picture about it. Okay, right now, quantization about momentum. Momentum quantization, quantizations. I'm looking for picture to illustrate that. Okay, here it is. Here we have picture here. It means the particle, the electron inside an atom cannot have any arbitrary orbit, cannot have any value of the distance of the radius from the nucleus, but the distance between the electron and the nucleus must be specific, must be like the floor in a building with certain distance, certain, defined distance to the nucleus, so that the wavelength associated with the movement of this particle, the wavelength determined by a formula in the booklet, which is called de Broglie wavelength, the de Broglie wavelength. Um, the formula for this wavelength is lambda equal Planck constant divided by the momentum, mv, momentum of the particle, the momentum of the electron moving in it. Okay, mv, the momentum, therefore will be equal to h over lambda. And another version of this quantization of the orbit of the momentum of the electron in the nucleus is angular momentum mv times r, or the radius, the distance, the average distance from the particle, from the electron to the nucleus. And here we have, you see here, it's like a wave, huh? A wave around the circus, the circle here. Basically, the radius that we are talking about, the distance from the nucleus to this circle is the radius of the orbit, and the electron is like a wave around that circle. This thing, MVR, is angular momentum, is equal to NH, a Planck constant. Sorry, N here is an integer 1, 2, 3, 4, 5. Okay. Uh, for example, when n is 2, that is the second excited state, divided by pi, huh? Divided by 2 pi. Okay. So R here multiply, we have mv equal to nh over 2 pi r. 2 pi here is the length of the orbit, the circle. Huh? Anyway, using this one, when the electron in the first excited state, n is 1, radius 4, wait. In the ground state n is 1, ground state n is 1. And then the second state, the first excited state, the radius is 4 pi, replacing r here by 4r, sorry, 4r, okay? N here must increase by, wait, the radius here. Anyway, change this formula a little bit, huh? mv equal to nh over 2 pi r here, 2 pi r. And the first excited state, n is supposed to be 1, huh? Because first excited state, n is 1. And then the radius is increased, the radius is 4 pi compared to the ground state radius is r. Replacing this one r by 4r, we have the new velocity. The new velocity must be uh, 1/8 of the old velocity, because we have no, 1/4, not 1/8, 4 times, yeah, 1/4, because there's the 4 here at the distance, huh? The ground state, the ground state, the first excited state, ground state n is 0. Let me check that. Bohr hydrogen energy levels. I'm wondering if n is 0 or 1 for the ground state. Okay. Let me copy this diagram of the energy of the hydrogen atom into the board here. Yeah. The ground state n is 1. The first excited state n is 2. Sorry, so the value of n here is not 1 but 2. 2. Therefore, replacing this one value to be 2. And we have 2 over 4. 2 over 4 is 1/2. And therefore, the speed of this first excited state is v over 2. V over 2, not V over 4. Okay. The next one. Nuclear reaction X plus Y equal to Z plus W involving nuclei X, Y, Z, and W energy release, which are correct about the masses and the binding energy of the nucleus. In a nuclear reaction like this, uh, it always happens in the direction so that the product Z and W will have the greater binding energy per nucleon. But the number of neutrons of nucleus of Z and W could be smaller than the number of neutron nucleus, meaning the total number of proton neutron of the reactants X and Y. Um, the masses, it has higher binding energy per nucleon. Assume that there is no change in the total number of proton and neutron, which means the total number of proton of and neutron of Z and W is the same as the total number of nucleon, proton, and neutrons of X and Y. So to have higher binding energy, there is some energy loss. It's called the mass defect uh, occurring for Z and W, the products Z and W. So the mass of Z and W will be smaller than the mass of X and Y, smaller, which means this one or this one. Okay, and we will eliminate A and B. The binding energy per nucleon, the same number of nucleons, so the binding energy per nucleon of the product is higher. It means the binding energy for each of the product also will be greater. The product binding energy, meaning Z and W will be Z and W will be greater, this one. So the answer is C. Okay, greater binding energy, greater binding energy per nucleon, assuming that the total number of nucleon of the product and reactant is the same. There's no loss in the number of proton and neutron, meaning no alpha particle, no beta particle. That could be a gamma decay happening at the same time with this nuclear reaction. One last question, huh? And then I need to do something else. Okay, two more questions. This is the small ball way up the attack to string, move vertical circle. What is the smallest kinetic energy ball at position X for the ball to maintain the circular motion with radius R? Okay, to maintain circular motion, it means that the ball here can reach to the top here again, reach to the top here again, without losing, making the string like it's not stretched anymore. It still have enough kinetic energy to stretch the string, making it there's a tension on the string. Okay. Mm, okay. Kinetic energy at the bottom. We have the radius here is r. So the distance from the bottom to the top is of course 2r. What is the kinetic, smaller kinetic energy but position x at the bottom? Okay. The kinetic energy at the top must be greater. At the top, the kinetic energy 1/2 mv top square must be greater than zero, meaning there's still some velocity, some speed at the top. And this kinetic energy at the top is equal, meaning mv top square will be equal to the 1/2 mv at the bottom at x square and added with the potential energy mg times 2r height. Okay, mg times 2r. So the smallest kinetic energy for at position x is when the energy at the top here is almost zero, and therefore that kinetic energy at the bottom is 1/2 mvx, where is equal to zero minus mg2r. Of course, the kinetic energy cannot be negative. Wait. Yeah, equal to this thing. Just ignore the negative sign. It means that it is the least amount, a least amount of, okay. When when Vx is zero, oh no. It has to have some kinetic energy so that it can keep moving up with inertia, uh, reducing the velocity Vx, reducing the kinetic energy of x, so that the kinetic energy can increase. Sorry, the potential energy can increase. Uh, and that least kinetic energy must be equal to mg times 2r, the potential energy at the top, mg2r, when the kinetic energy at the top is almost zero. The minimum amount of kinetic energy is here. This thing is minimum when it is equal to the potential energy at the top. Okay, and therefore Vx is calculated by this thing. Simplify m 2gr 2gr and then multiply by 2 4gr, 4gr and square root, meaning 2 square root of gr. So the answer is, oh, the question is kinetic energy, not the velocity. Sorry. So the answer is this one, 2 mgr. Let's rewrite that, 2 mgr. And mgw, the weight, okay? 2 wr, the weight. So the answer is this one. One last question here, huh? Capacitor charge current is 2.5 microampere 100 seconds. As a result, potential difference across the capacitor increased by 5 volts for the capacitance of the capacitor. Current time. The product of the current and time, constant current, it is not realistic because in reality the current will decrease when charging like this. Not a constant, but anyway, this is an assumption like taking an average current. So the charge that the capacitor store is the current multiplied with time. We have this equation in the topic 5. The formula is the current is the charge over time, and from this formula we get to this formula. The charge is the current multiplied with time. Okay, and that current is 2.5 microampere times 10 to the negative 6 to convert into ampere. Then multiply with the time 100 seconds, we get 2.5 times 10 to the negative 4 coulomb charge. Capacitance C. Capacitance C is the charge over the voltage. So we have this charge 2.5 times 10 to the negative 4. The voltage is 5. So dividing this, we have 1 half. So it will be equal to 20 microfarad. This one. Micro, not milli, huh? And why do we get to that from negative 4 to negative 6? You can figure it out yourself, huh? 20, definitely. Okay, that's it. I will help you to solve all the questions below later, next time when we see each other again.